Hi everyone, I'm Toby Shockman. This presentation is about a different way to program computers. So the seed for this thesis project was planted the summer before I came to ITP. And that summer I went to the first ever Emerging Programming Languages conference. And at this conference there were about 30 speakers, each of whom was the creator of a new programming language. And they talked about why they created a new programming language, what made their programming language different than what's currently out there, and the various issues that come up in designing a programming language. And I found this whole conference to be fascinating, especially the idea that with the new programming language, we could radically change the way that we program and the programs that we create. So during my 2 years at ITP, I've always had in the back of my mind this idea of rethinking the way that we program. So programming hasn't really changed a lot in the past 50 years. I'll qualify that. We've gained deeper experience programming in a certain way, but the actual way we program and the modes of thought that we use while programming are the same as they were 50 years ago. We write our programs as lines of text, and with each line we're essentially micromanaging the computer. We're saying, do this, then do this, then do this, then do this. And this way of programming is so ingrained in our consciousness that we usually don't even think that there might be another way, another possible way to program computers. We're stuck on the bottom of this canyon. We can't see other possibilities. And I think there are two reasons that we're stuck in this rut. The first is the tools that we have. So our existing programming languages encourage certain ways of thinking about programming, and the new programming languages will just emulate the old ones and further propagate these ideas. But the second reason is more subtle, and that's that the programming community itself self-selects for people who think in a certain way. So if I happen to be very good at thinking logically and sequentially, then maybe when I start programming I say, hey, this is pretty easy, and I become a professional programmer. But if all of our programmers are very good at thinking logically and sequentially, then this reinforces the idea that programming has to be logical and sequential. So if we want to radically change how we program, we need to target those changes at new programmers, fresh minds. As it happens, I believe we are witnessing the emergence of an entirely new generation of programmers. These programmers don't come from the traditional computer science education, but instead come from unlikely backgrounds like design and the arts. And ITP is a mecca of sorts for this new generation of alternative programmers. A lot of the ideas that I'll be talking about next in my presentation come from my interactions with the ITP community. These diagrams here are from an early user study that I did, where I asked participants to draw a picture showing how the interactivity in their project worked, without making any reference that this was about programming. There are a lot of interesting results from this that I won't have time to go into in the presentation, but I'll give a URL at the end with all of these diagrams and some commentary. So some alternative programmers just take to programming and they do it just fine, but other times I would notice that there seemed to be a cognitive dissonance, a mismatch between how the person likes to think and likes to work and how the programming tool expects the person to think and work. So, for example, programming is a turn-based experience. The programmer types some code, presses run, and then the computer does something. The programmer observes how the computer behaves, adjusts some code, fixes a bug or whatnot, presses run again, computer does something, and this cycle repeats. So contrast this turn-based experience with a continuous feedback experience that, for example, a musician would be used to. So a musician will manipulate her interface, the instrument, and will experience the results of this manipulation in real time, continuously. And even more important than supporting alternative ways of working, our programming environments need to support alternative ways of thinking. So traditional programming tends to be, it tends to sort of encourage this accounting-centric mindset. So the programmer is managing a bunch of values, moving the values around in the program, adding the values together, multiplying them, incrementing numbers. Sort of traditional programming is founded on these accounting tricks. Yet most of our most profound and creative ideas come when we're thinking spatially. And this applies both to the arts and the sciences. So contrary to what we learn in high school, mathematicians and scientists don't spend their days writing down numbers and equations. They build models, they draw diagrams. And they do this to build a spatial intuition for the problem that they're attacking. Visual programming environments don't necessarily encourage this spatial mindset that I'm talking about. So you may be familiar with the patch-based languages like PD, MaxMSP, VVVV, Quartz Composer, etc. And these are great, especially because they support the continuous feedback like I was talking about earlier, but they don't actually engage the programmer spatially in the way that I'm talking about. So in this example, the programmer is doing something spatial, deforming some geometry, but to do this, she needs to use the accounting paradigm. And the code is laid out spatially, but the spatialness of how the code is laid out is irrelevant to the spatialness of the problem that she's working on. So here's an exception that proves the rule. So this is a PD patch for doing Kinect skeleton tracking. And the programmer has laid out her patch to resemble a human form. And each of these groups of boxes corresponds to a joint in the skeleton. But PD doesn't naturally encourage this way of laying out your program. This is just the result of the programmer being a particularly spatially oriented thinker. So now I'm going to show a demo of some user interface ideas I've been playing with over the semester that I think encourage a very spatial mindset. So this is called recursive drawing. Here's how it works. So this is a canvas, and I can drag shapes into this canvas. I can move the shapes around. I can rotate and resize them. And the shapes that I create here are themselves shapes that I can use. So if I make a new shape, I can drag this heart shape in. And everything is live, so if I change this original shape, then all of the instances of that shape change as well. This area over on the right just shows me the components that make up my current canvas. So these heart shapes are the ones that I put down, and I can expand them to see the shapes that they are made up of, these circles and squares. So now the interesting thing here is that a shape can contain itself. So I'm going to start with a circle, and now I'm going to take this shape and drag it into itself. So what's happening here? So we have this original circle that I put there, and then we have a copy of the entire shape itself. And the copy consists of a circle and a copy. That copy consists of a circle and a copy, etc. So this is a recursive shape. If I change the original circle, then all of the other circles will change with it. But if I change the copy of the shape, then that transformation propagates down recursively. So I can scale this and rotate it and create these spiral shapes. And I can do this at any level of the recursion depth. So I can move this one around, rotate it, etc. So here's another example of a recursive shape. I'm going to start with a square, turn it into a rectangle. Then I'm going to drag the shape into itself. Now I'm going to drag another copy of this shape into itself. And I get this tree. So this is just a recursive shape. It starts with the trunk of the tree, and then there are two branches. But both of the branches are just copies of the tree itself. So I can show that by expanding here and showing that this branch is made up of a trunk, a left branch, and a right branch. This type of interface encourages a certain sort of exploration of the possibilities that wouldn't really be supported, I think, in a textual programming language for creating a shape like this. So for example, this is a binary tree, right? It starts with one branch, and then each branch makes two more branches. So it goes 1, 2, 4, 8, 16, etc. You can see it in the shape. So I was wondering, would it be possible to make a Fibonacci tree? So the Fibonacci numbers go 1, 1, 2, 3, 5, 8, etc. This is a sequence that appears in math a lot and in nature. You derive it by just adding the previous two numbers to get the next one. So how would I go about making a Fibonacci tree in this interface? So really all you have to do is play around a bit, and you can figure these things out. So I discovered just by playing around that I can just take this branch and move it up a level, and then I have a Fibonacci tree. So it goes 1, 1, 2, 3, 5, etc. So recursive drawing isn't an end in itself. It was just an experiment to try out certain user interface ideas that I thought would be useful in this vision of a more spatially oriented programming environment. So my immediate next steps will be to put recursive drawing aside and try some other experiments to dig deeper into some of these user interface ideas. So here's an example. So the way that recursive drawing works is you're essentially creating spatial relationships between shapes. And then these spatial relationships combine with each other to create the behavior, like make that tree. And this can be very powerful, I think. So for example, say I wanted to make an interactive animation like this. Instead of typing up code to do this, I think it would be nice if I could just put some circles down and then put some relationships between the circles. So I would say this black circle always has to stay within the white circle. And I'd also make a relationship between the black circle and the mouse so that they always tried to keep the minimum distance between each other. And just by declaring those relationships, that's actually enough to completely specify this program. So I've been showing graphical examples of this programming strategy, but I think it also applies to other domains. So these are all diagrams that I pulled from the Wikipedia pages from various machine learning algorithms. And as you can see, when programmers describe an algorithm to each other, they do so spatially. We even use spatial terms in our vocabulary. We'll talk about search or hill climbing or clustering or nearest neighbors and things like that. So it would be nice if we had a spatially oriented programming environment which would allow us to define the behavior of these algorithms to the computer also in spatial terms. So after I went to the Emerging Programming Languages conference, I went to go see this movie Inception with a few of my friends from the conference. And if you haven't seen this movie, it's basically a sci-fi that's premised on a technology that allows people to have shared dreams. So what would a programming interface look like that would allow us to construct shared dreams? For me, this is the long-term vision of this project and where I would like to see programming go. Programming as a multiplayer, multi-programmer, real-time immersive experience where we're discovering a world as we're creating it. Thank you. And you can try out recursive drawing at recursivedrawing.com and see those, that user study at itp.recursivedrawing.com.